Hello, and welcome to Summarize Science. Scientists use computer models to understand everything from predator-prey cycles in an ecosystem to the spread of a new virus. But a huge challenge is tuning the knobs on these models to make them match the real world, especially when the underlying math gets incredibly complex. This paper presents a practical guide to a powerful method that sidesteps this complexity, called Approximate Bayesian Computation, or ABC. Instead of solving difficult equations, the ABC method works by simply simulating the model thousands or millions of times with different settings. The computer then checks which of these simulations produces data that looks the most like the real data we've observed. Essentially, it finds the right settings by playing a giant game of hot and cold until its virtual world matches our world. The specific technique highlighted, called ABCSMC, is a much smarter and more efficient version of this. It starts with broad guesses and then intelligently focuses its simulations on the most promising settings, saving massive amounts of time. To see how this works, let's look at a classic model of predators and prey. In this first example, the researchers pretend they have data for both species, shown by the blue and orange dots. The model quickly hones in on the right parameters, and the simulations it produces, shown by the solid lines, perfectly capture the real dynamics. But here's where it gets really interesting. What if you can only observe the prey? This is a much more realistic scenario, as predators are often elusive and hard to count. Amazingly, even with this incomplete information, the model can successfully reconstruct the hidden predator population. The model infers the rise and fall of the unseen predators just by watching their effect on the prey. The researchers then apply this exact same idea to an epidemic model. In disease modeling, we can often track the number of susceptible, infected, and recovered people, but the exposed group, those who are infected but not yet infectious or symptomatic, is usually hidden. Just like with the predators, the ABC method successfully reconstructs the dynamics of this unseen, exposed population. You can see its estimated trajectory here as the red curve. This allows for a much more complete picture of how an epidemic is truly spreading. The final example shows how this can be scaled up to a hierarchical model, for instance, when analyzing outbreaks in two different cities. This powerful structure allows the model to learn about each city's unique dynamics, while also learning about the properties the epidemics share. It enables a city with very little data to borrow strength from a city with better data, leading to more stable and reliable estimates for both. The model figures out both what is different and what is the same across groups. So let's recap the important points. This research provides a clear, practical guide for a technique that allows scientists to fit complex models to real-world data, even when that data is incomplete. It demonstrates that we can reliably estimate the dynamics of hidden variables, like unseen predators or silent disease carriers. And it shows how to use hierarchical models to analyze multiple groups at once, improving the accuracy of our conclusions. What does this mean for the future? By making these powerful simulation-based methods more accessible to researchers, guides like this could help accelerate progress in many fields. This could lead to more accurate ecological forecasts and better-informed public health policies for managing future pandemics.